Good.
Will begin shortly. So today we have one patient here, Dr. Johan's home, and he's going to share his experience in physics learning and also exploration. And this includes the experience before and after the journey to America. He will cover some questions like why did I choose to study in the US? What were the difficulties that I encountered? How did I prepare myself for the graduate study? So, and also how did I overcome the challenges? So in this one, we will talk about the path that we took from a high energy theorist to condensed matter experimentalist. Dr. Yu is getting himself in the how Dr. Yu getting himself in the highly competitive research field. In another words, topological insulator and also superconductor. So this will include a quantum physics as a brief introduction. So I saw some of the students are okay. So I think still okay. So you no need to take the quantum physics as prerequisite to understand this today's talk. So yeah, Dr. Yu Kari is associate professor in Missouri University of Science and Technology, specialized in material synthesis and condensed matter experiment. Before joining Missouri University of SMT, Dr. Yu was working at Arizona National Lab and Princeton University as a postdoctoral researcher. So without further ado, we'll invite Dr. Yu to share experience.
Thank you so much to Jian Hao, right, for the very nice introduction. Uh, it's, it's great to see the old friend from UM. I'm sorry I forgot all your name, but still to recall my memory. So, Yun, yeah, Yun, Dr. Yun and Dr. Wong. Yun. And probably not from UM, right? You're still. You look like professor. Again, thanks to Jian Hao for inviting me, and I think it's a good opportunity for me to come here to share this experience, my experience in Malaysia, UM especially, and the experience in the United States, and how now I prefer to have something like to excite you or to stimulate your interest in doing physics here or abroad. I do not want to steal your student. But in the last part, I'm going to talk about how to get admitted to the US universities. All right. Okay. So this is the outline. I think we have 4 parts actually. So first is the life in Malaysia. So of course, the question you might ask, why I'm interested in physics, or maybe you have your questions yourself, right? Why you want to do physics? Because your parents force you to? Definitely not, right? So basically, for me, it's just interest. I'm interested in doing physics. Most of you, I believe so. So when it comes to physics, you don't tell me that you do physics because your parents force you to do. I don't believe that, right? So now, why I'm interested in physics? So I have to go back to the very young age of me, and I think probably it's before my elementary school. So I actually like to see the it's curiosity. I like to see something like different, the crazy thing, like the strange thing, a new thing. So, for example, my uncle bought this used car long time ago, and the car was very old, right? Exactly, it's the same like this one, right? And then it doesn't have to use key to start like our new car today, so they have to use the crank self, this kind of wrench, something like this person doing, right? Maybe it's good idea. I will. It's okay. I think maybe I need a pointer or something. All right. My hand is not long enough. So you have to crank this to start. And then it's really interesting. And then it's a little bit dangerous to do so because of kicking or something. So I I kind of interested in finding out why this car is moving, right? So I tried to observe. I think that was probably at the age of 5 years. I think 5 years old. I still remember a lot probably. And I observed, and then when the car moved, its exhaust like give out a cloud of smoke, right? And that's I in my mind is I thought, oh, probably the car can move it because it's propel those smoke out at the back, so it's going to move. So I have that kind of thinking that time. So and so this is how I try to figure out why and how and what. So at the age of 5 years old, so I think I like to know science, right? So besides, I also interested in other stuff like electronics. I learned the electronics, for example, chemistry, watch repaired from my father. And my father actually did not go to any school. I think he just have these. I think maybe you can call the primary school, maybe 1 year. That's it. And he learned to read Chinese, and he bought a lot of books, electronics book, these radio books, and he studied by himself. And that's why probably I get influenced by him also. He also has chemistry books in Chinese. It's totally in Chinese, and he taught me how to repair watch when I was maybe about standard 6. So I learned all these things from him. I still remember I also interested in woodworking. When I was like probably about 5 or 6 years, I still remember I cut myself. I cut my feet with the saw, and I was so scared. It's really deep, bleeding a lot, and I did not, tell my mother because I'm afraid to get scolded. So, all this happened. So from science and also from the go to arts. So I like all those things. So if you ask me why I interested in physics, I think it's because I'm really interested in figure out why, what, and how, right? Of course, the question I have when I do physics, so I think you probably have the same experience. You start to know physics in tingkatan 4 or tingkatan 3, tingkatan 4, right? From 4, right? Start to know, oh, there's a physics, and I really fell in love in physics. So I read the books and I listen to the class. Of course, the first equation I encounter is F equal to ma, right? But that is not really like interested me a lot. But the most interested me is I try to answer that kind of question. What is light? I'm not sure you have that kind of question yourself. So that was in Form 4, Form 5. So I want to understand what is light, and at that time I had this idea saying that light is particles like corpuscle, all right. So later on we're going to talk about it. Now, of course, I have this one. I thought I know how to explain about light, okay, but later on you see I was wrong. And then I have a lot of questions, especially when I came to high school. You have STPM. All of you gone through STPM, right? Me too. That was a really nightmare for me. I do not know whether you have that kind of experience. Well, why? Because I have this language barrier. I, you know, go through this Chinese school in elementary school, primary school, and in what they call this middle school. I don't think you call middle school, but from 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 remove, I went through remove from 1 to from 5. I learned all this Malay, so use Malay as a medium. So when you come to Form 6, and there is a limitation for physics book, because it's higher level, and then not many translated book in for physics. So each time I read, I could not understand what it means. For example, when you touch about this, I don't know, funny name, Chakrapadat, something like that. Well, Chakrapadat is for computer science. Hard disk chakra. So something, those translation, I got problem, right? So I try to ask a lot of questions. And of course, I read a lot of books by myself, as the physics book, and that's the cartoon I have, experience that I have. I asked the teacher, all right, apa ni, apa tu, right? Now, of course, due to the culture, we have that kind of hesitation to ask questions. Am I right? I'm not sure whether you ask a lot of questions to professor. Maybe Dr. Wong, your student asks you a lot of questions. Now, what's the teacher reply to me? Do you have the same experience like this, like what I had before? Okay. So maybe the response is, to me, I feel relaxed a little bit. Oh, so I don't have to study. But certain things I want to know, but somehow I just wait. I just wait until I get past the STPM, and then I go to college and then do physics, right? But I got a lot of problem. I'm not a smart student. I'm not like my friend. They can get a lot A's. For me, I got a lot of these difficulties. For example, my language is not good. I flung my kertas arm. F, fear. So I retook. I got an A. I didn't study for kertas arm, but the next year I got A, and I did not know why. Until now, I do not know why. Okay, so of course I got admitted and as a super fresh, and then I met Dr. Wong. So he was very nice to me. He got the bike and carried me all around the campus. Yeah, so I need to say thanks. Experimental partner, yes. Well, we have done a lot of this experiment for second year lab, right? All right. So now, okay, that's very good. It's college life. Now I still have a lot of questions. Apa itu, apa, mengapa ni? All right. Why, what, and how? Right. All right. And the same question. The only difference is that maybe my hair is longer. And the teacher now is professor, a little bit fear, a little bit serious. All right. And what is the response now, you think? Do you have that kind of experience, Dr. Wong? Actually, it's my advisor. Maybe Dr. Yun will know. No. So I did not know what to do. So now, actually, that time I realized it's a usefulness for having a long hair, like Zheng Hao, cover my face. A little bit shy, right? So now I don't have hair to cover face, so I have to grow my thicker face. So you have to hold P, so that you can keep asking questions. All right, so this is a little bit what I call this interesting part of my experience. So of course, you try to learn things, and from 6 STBM is about classical mechanics, classical physics. You have not learned about quantum physics. When you come to college, you have to learn quantum mechanics. You still remember? I think I did very bad. What is your no, I think it's Buharurin, someone else. So I think more than half of our class fail, is it? Fail. So I did very badly, and I have no clue. You know, I don't understand at all what is quantum. You see, so that is the experience that I had when I in college, and I cannot learn this quantum mechanics by reading book anymore. If I read this one, I saw equation. You see, a lot of equations. Okay, let me see what is this next slide. But I was very good in experiment. So I remember you do nuclear physics, and then I signed up for this plasma experiment for our final year project. Yes, so I was really good in this experimental hemisphere. So I built those what they call the rotomark. You heard about tokamak, and rotomark is invented by this Australian university, and you know the Professor Lee Sing, and he actually was my not mine. No, he was not. But when I tried to take out this project, he was the big boss, Professor Lee Sing. He's very famous. So he tried to get. Oh, what is time now? Maybe I talk too much. Okay, all right. Thanks. And then he wanted to build this rotomark. Rotomark means a machine that they try to use the magnetic field to confine this plasma, so that we can have this what they call the plasma fusion. All right. And I built those things. I wind a coil to produce this magnetic field. Of course, I didn't generate. I did not build those amplifier. Jasper, you still know that person. Jasper built those amplifier. Then amplified the current. We need to have the high current, oscillating current, to generating this oscillating magnetic field, and then coupled with the Helmholtz coil, we have this field, and then form the very beautiful this what they call the field configurations. They call this I don't know. I think this is also rotomark, like rotating field, and nobody can explain those how this field configuration can be generated. So I did those project for my final year, and then in the thesis, so I include this explanation how this field configuration can be formed. So I didn't use equation. I just used the diagram to draw the magnetic field, how the magnetic field interact with each other, and then you can see those field configuration that can confine the plasma. And of course, we have to go through this test. The exam means YWA. They call YWA. It's really a painful, also another nightmare. So I remember my advisor is the late Professor Cheng Yu Ho, and also Harik, and the big boss. So the big boss, Professor Lee Sing. And of course, they read through my thesis, right? And nothing special, but Professor Lee Sing got impressed about the explanation. So he said, "Oh, this is good. This is good." So this is one thing that I feel great about it. So it means that I did very good things for that project, even though this maybe not correct us. But he was impressed by the explanation, and this is one good thing. So the experience that I had, I want you to know that try your best, try to explain You know, use what you learned from your high school, from your kindergarten, whatever, and then try to apply to answer only 3 questions you might have in your brain, right? Why, what, and how. That's it. So maybe it's wrong, but at least you try, right? Um, so this is Professor S. Picha, but I didn't continue to work on this plasma experiment. So I want to do something else because I want to answer the question, what is light? So I went to see Professor Chia, my master advisor. He he always asks a lot of questions. Why you want to do master? Why? What is because this high energy physics is something about elementary particles. Can you define what is elementary particles? Of course, I got the answer, and he said no, 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 no. All right, I still remember I had this question from him. What are you interested at? What topic do you interested? Are you interested in? Right. So I say, oh, something about this light. Oh, I want to solve this problem called duality because I read about this duality. So I don't believe that the light can be wave or can be particles, something like this. So I want to figure out what is light. This I want to answer the question. But the really what they call sad things that he say, oh no, this is old problem people already done. So I cover my face with my long hair again. Okay, so this is really desperate to have, but eventually I joined him. He accepted me as his student. You still remember the book, Bioker and Rio, right? Yo, not BJ. Bioken. Okay, thanks for correcting me. Volume 1, yeah. So it is not about quantum mechanics, but the relativistic quantum mechanics or quantum field theory. So for the whole master program, I just read 2 books. These 2. Why? Because I got the the English barrier, the language barrier. I could not understand. So that is the drawback of my part. I like to like to learn things, but you see, when I come to read the book, I do not know, Dr. Yuan, how long you spend to read 1 page. I spent 4 days. The first page about the Dirac equation. Really? So I'm smarter than you? No way, no. No. I think the difficulty is that the calculation. I think we have no clue how to derive the equation, how to verify the equation. So we have to. Luckily, I have my best friend, Tseng Ping Chun. He's a really motivated guy. Well, because of him, I keep moving, do not stop. That means keep reading. Because 4 days, read 1 page. I have to go back to read a lot of this dictionary. Not like nowadays you have the, easy chat GPT and everything you can understand, right? So this is the difficult I have at that time. But I never give up because the friend and of course I learned something from my friend, mostly not from SPCHA. All right. After this, of course, we have done a very good work in this high energy physics theoretical work. I'm sure Dr. Yun also produced some decision work. in high energy theory? Still keep your calculation? Exact, they call it exact calculation. Wow. Very long, right? We all use the paper, do a lot of calculation. And sadly, we don't understand at all what it means. We do not understand, for example, those operator, those wave function, or CAD, all those things. We just know how to do calculation, integration, calculation. All right, and now you do computational physics. So well, at the time I didn't really like want to go abroad, right? Because I can do postgraduate study in and they are good. Professor Spicha, they are good, and couple of professors, they also very nice. But I want to learn about this, quantum mechanics. I really want to understand, not only just doing math. So I want to understand what is phi, what is this, how, why, things, this three questions. So I went to take this quantum mechanics under this the late Professor Fong. So he's a math professor. So also doing math, of course. But I attend his class, and he also really feels but a good professor. So he encouraged me to go abroad. He said, if you want to do a good research, go abroad. Don't stay in Malaysia. I'm sorry to say this, not for me, from him. Say, all right. So in Malaysia, you can do a high quality research. I think I now I understand him, because here now it's about environment. Now you guys are smart. I'm also like little bit smart, right? I cannot say we are stupid. No, we no stupid word. So you have to find what you are interested at, and then you have to have the patience. All right, and then you have to be very hardworking. Go for it. All right, work for it. Now, of course, you can achieve that level. Why? Because you don't have this environment. You have no people to talk to. All those top people are in the US or in Europe. Maybe you can find a few in NUS Singapore, but it's very hard to find the top scientists in Malaysia, and you do not know what they want, right? So you didn't do something like people have learned a little bit, and Professor Fong say these are toy project, like for fun, not for some real research. So he encouraged me to go abroad. And Professor Chia, of course, I talked to him. He say, ask a lot of questions. You have to ask yourself, are you interested in doing research? And then I kind of don't know. So I asked him. No, he asked another question. Do you think you have the ability to do research? I also don't know. And I asked him back, Professor Chia, do you think that I have the ability to do research? And he never give me the answer. He said, you have to ask yourself. And then Professor Lee also very nice, and he's good in quantum mechanics. He actually graduated from Rochester University, US. So I also asked advice from him. So I say, well, I do not understand quantum mechanics. I cannot, maybe I cannot catch up with them. And Professor Lee is like encourage me. Just go. Don't worry too much. When you get into the class, you will slowly learn step by step, and then you can catch up the pace. So okay. So someone had encouraged me. Someone had give me some hope. So I just do preparation. This is what I prepared. GRE, TOEFL, and I'm not good in English. So friend teasing me, you're not going to go to US because your English is very lousy. So I spent like more than 2 years preparing all these tests. All right, and I think now you are better than me. your English is better. So, so I prepared many times. Means I took the test many times. I could not count. Maybe I should use two hands to count. And it's not cheap. The application fee is very expensive. You can check. And I managed to get not really good, but above maybe 70%, 75% for physics test, considered good. General test is a little bit low. I think it's below 30%. It means that the 100 students take the test, you are like below 20%, something like this. You're not the top. But I managed to get the admission to Utah State University, and the Utah State University didn't give me any financial aid, means no TA. So I had to prepare money, about $15,000 for 1 year. So I went. And then the second year, I managed to get a teaching assistant because I passed their TA workshop, teaching assistant workshop. So I have to go through this the training to speak, to listen, and then to teach by using English. So I passed. Then, of course, I went to America. So this is the movie I had that time, 1998, when I was in the US. So, of course, when I arrived in the US, not like this romantic story, all right? It's a little bit weird. This is the first impression I got about America is less deserts. All the trees are dead. During that down, like, well, because I went there in September, and I think in Utah they have the very early winter, so all these the trees like high in hibernation. So, but I did not know. So I thought America is like this, dead trees and boring place, no romantics like what we saw in the movie Coming to America. Of course, I went through those the classes, the culture, and things like that. So I still remember I took. Maybe let me see if I go back. All right, I took quantum mechanics, classical mechanics, electrodynamics, statistical mechanics. Though I consider Bibles of physics. So it's for the graduate school. So you have to master all those knowledge, and then you have to pass the qualifying exam. And then of course I will go back to this slide. Let me tell you one thing. So Malaysia students is like, oh, you have the exam, you go and study and then find the past year question. Am I right? Study the past year question. And then if you have homework, you just try to copy from your friends, right? Or you can find the problem maybe online, something like this, and then you copy the solution. So at the time, I was first year graduate school over there, and then of course you mix around with the Americans classmates, and then I saw they are staggering. My American classmate friends, they are struggling to solve problem. I say, why are you so difficult? Don't make your life miserable. So I have solution for you to copy. I said, no, this. I do want your solution. I want to do it myself. So this is the first impression I have about Americans. They really want to experience themselves. So, for example, when I do the experiment, I saw this gas tank living there. So I just take without any permission. And then my friend said, you cannot do so. You have to ask permission, something like this. So this is their culture. I think they built out those, I don't know, maybe the culture very long time, or maybe they done it when they are small. We do not know, right? But they are really like honest. They they want to do it themselves. They do not want to copy your solution. Okay, so of course I did not continue to do high energy experiment. I changed because uh, when you want to do high energy experiment, you have to travel around to the whole world because the experiments is very expensive. So I switched to do condensed matter physics. Of course, when I come to this problem, I still interested in figure out why, right? What is light and why and how things like that. Um, but most of my PhD work is in chemistry and material synthesis. And I try to tell the story to my, for example, when my parents asked me, what are you doing for your PhD research? And I told them, it's like you, mom, baking cake. You just mix flour, you mix sugar, mix, and put in the oven, and then bake it, and then come up, all right, you taste very good or bad. Easy. So material synthesis is just like this, all right? You mix, for example, bismuth selenide, you mix bismuth element, selenium powders, mix, seal it up. Of course, you need to seal, vacuum seal, and then put it, we call furnace, not oven. So you heat it up, and then melt, and then you slow cook it, and then come up with crystal. Of course, you don't put it in your mouth to taste, right? So you test it by using the machine. Okay, this is the material science. This is my project for Argonne National Lab for Princeton University. I'm very good in experimental skill. So this is my what I call this. Everyone has one, right? So you good in maybe speaking, public speaking or something. So you try to find yourself this what you are good at, okay, and then amplify it. So I was good in that. So when I do my PhD projects, my advisor, Professor S.W. Chung, he didn't want me to do measurement because you are good in this. You do all these things. Keep doing this. Keep this. So I produce a lot of these samples, crystal, for those, for example, superconductor, semiconductor. Now become topological insulator. So when I was in Argonne National Lab, I grow all these nanowire, nanomaterials, and then someone wanted me to, my boss, Professor Kawa, he wanted me to do some thermoelectric materials. So I went, and at the time I grow all this beautiful crystal for bismuth antimony, I think that time only bismuth antimony. And luckily that 2007, I went there, I went to Princeton in 2006. And then 2007, someone predicted that this bismuth antimony is a 3D topological insulator. So what is that later? I'm going to tell you what is topological insulator, what is topological materials, all right? So we're going to touch a little bit on that. And that time I already have those beautiful crystal, and then someone just take it and then test it, and then so, oh yeah, it's a topological insulator. Suddenly the whole world is rocking. All right, wow, we're going to have the breakthrough. We're going to have this quantum computer, something like this. So at the time, only two groups are considered very top in the world in this research. One is Stanford University, led by the So Chen Chang. They are doing theories. And then Princeton, led by, I think, Jahid Hassan, is experiment. So my part is just grow crystal materials. So we grew a lot of these high quality crystals for them, and we got a lot of these nature papers, and we become famous. All right. So So easy, just like baking cake. All right. So I'm sure you can do that too. Just concentrate, be patient and hardworking. Baking cake with the lemon juice, and then one day you'll get famous too. Oh, all right. So of course, those are these material science condensed matter experiment. I got a little bit famous because of that, right? With having those beautiful crystal. But my what I call ambition, still I want to answer this question. So and then I of course did a little bit study for my master degree in Utah State University. So I wrote this theory also without equation, with just diagram to explain why there is a quantum entanglement, why there is the wave particle duality. I explained that. So this is in my USU master project papers. But of course I got A. I think the professors just trashed it. So I still keep that project, but it's a long story. I'm not going to tell you here, but I'm going to tell you the history of this to answer this kind of question. Now, people also think very hard about this question. So especially Newton, when is it? 1601 to 1700. So that is the era Newton and Huygens, two big shots, try to answer the question. But who wins? Newton wins because he's the most famous in that time, right? So everybody believe, oh, light is particles. And then come this guy, Thomas Young. I'm sure you heard about it when you do physics in high school in 1807. Thomas Young is genius. It was genius. He actually was a doctor trying to, cure patient, and one of the patients has a problem with eye. And then Young tried to solve the problem and then tried to study optics. And because he's genius, he come to the question what is light, and then he has this idea, and then perform the experiment to tell you that light is a wave. So this is the double slit experiment. So this is a very interesting experiment. Until now, still people do not understand. Still needs you to explain that. And then you have the Maxwell equation. All right, this Maxwell equation try to tell how to generate light. So light is the electromagnetic wave. All right, so you can produce this light or electromagnetic wave. So that's why you have this iPhone, U phone. You have iPhone, I have U phone. So all those phones are in this using those Maxwell equation. Of course, you have to thank this another guy called Hertz. So he can use the theory and generate this electromagnetic signal, microwave. So now you have this microwave flowing around with your phone to phone. And then in 1900 come with the Planck. Now this changed the history totally. So you say now you cannot use wave anymore because when you come to the interaction, so there is you so-call this light has not sufficient to excite the electron. So there's interaction there, and those the light actually you must have enough energy. So they name this light as the package of energy called this H is the Planck constant times the frequency. So you must have enough energy so that you can you can talk, right? No money, no talk. So no energy, no talk means you cannot excite this electron, something like this. So this is something to do with this understanding of what light is. Okay, and then Einstein have this photoelectric effect, right? Light come in and then it can kick out electron, and then you might have the certain energy of light. It's not like the classical interpretation of light. The classical interpretation of light is something to do with intensity, and the intensity cannot kick out this electron. No matter how strong the intensity is, you cannot have any photoelectric effects. The photoelectric effect is only depends on this energy of the photon, called the particles. So Einstein had this theory. He won the Nobel Prize, and suddenly everybody is thinking of particles again. So what is light? Light is particle. We call photon. Now, what about this young experiment? Clearly proved that light is wave. So we have no choice until this de Broglie come up. De Broglie also kind of famous. He say everything in the universe, including you, is also a wave. You are made of wave, right? So it's very hard to accept. Am I right? So when I do this high school physics as TPM, they touch a little bit matter wave, and we cannot accept this concept. So now come to the idea of duality. It can be wave, can be particle. It also cannot be wave, cannot be particles. So this is the stage of quantum mechanics. So we're going to say a bit more. Do we have time? Oh, it's almost. Yeah, if you're watching movie, yes. All right, let me quickly finish. All right. Okay. So this is something to do with quantum mechanics. So I'm going to touch a little bit of quantum mechanics. But before we go on, because my title is from classical to quantums, right? From Malaysia to America. From classical, so we have to talk about classical. So classical mechanics, you have learned all this, right? F equal to ma, things like that. But we have no clue what, why, and then how, right? What it means? What is F, right? For example, what is M? What is A? Something like, all right. So F is force, M is mass, and A is acceleration. And why? Do you ask yourself that kind of question? Why? I ask myself that kind of question, and because of this, I do know about F equal to ma. I always have difficulty to solve physics problems, so I have to memorize that. So actually, it's very simple. All right. So it's just a physics. So what is physics? Do you ask yourself that kind of question? So physics actually is something like what I had in the beginning. See this, my uncle's used car is moving, and you have to see why it's moving and how. So that time I was young, I say, oh, because it has exhaust, then it move. Because of this exhaust, propel the car to move forward. That kind of thinkings, right? But of course now I understand there's engine. So that must be something. So for physics, actually, when you study physics or understanding physics, actually understand all the question. So we are interested in the movement, right? And the movement, for example, this car is moved, and then we should know how, right? We should predict in the future. So if this car moves with 100 kilometers per hour, so I'm going to know that in the future it's going to collide. It's going to have collision, something like this, right? Something prediction. So same thing. So you need to have this all bunch of equation to tell what will happen for the car. So the location, for example, x, direction, velocity, all right, and then how fast, and most of the things they should talk about energy, and all this is based on this A, right? Something is different, all right. So this A is acceleration. Now A let me explain this A. So you know acceleration, but to my explanation to you is the change of state. The change of state. What state is the velocity change with respect to time? So if you have change, all right, then you have acceleration. Change. This is about change. So this acceleration is caused by the force. So make it simple. If you have the force, you're going to have change. Or you have the change, you're going to have force govern. All right? So for example, if you sit here, no change because no force. Right? If you have force, you have change. Or if you have change, means there must be a force. And then you ask the question, where's the force come from? Or what is force? All right? Where's the force come from? So the force come from this potential difference. Have you thought about that? So what is the potential? Then you ask, and you keep asking what and how. So something is something to do with the potential difference or something difference. For example, temperature difference. What happens if you have temperature difference? You have the flow of air. You will have force. What happens if you have this the idea difference or the opinion difference between you and me? What will happen? We will fight, right? We will force. This is something about that. So this is about the classical physics. But when you talk about this quantum mechanics, they will not talk about force anymore. They will not talk about this potential difference. They talk about just energy. So the system is all energy. Everything comes to a very simple case. If you know classical mechanics, of course, we talk about energy, Lagrangian, Hamiltonian. So this is all about energy, but quantum mechanics is more than that. I give you the equation. Probably you have seen this one, but you don't have to understand all these things first, okay? So I just want you to tell you that this quantum mechanics is something about also the state. It will not let you to understand the movement or the particle, where's the location. This quantum mechanics will tell you so about the state. For example, if you want to know the position, you apply the x. Now, what is x actually is observer. You want to, you're not seeing, you're like observe. More than seeing, observe means you can have detect, you can measure. All right. So all these terms that you can have. So when we talk about this observer or operator, people like to say, okay, the wave function is collapsed. This is the psi. This is state. Now, people call that as a wave function. Sometimes people call it as a state. So, for example, this observer, we call the Hamiltonian H. So, you want to see how much energy you have. So, you're going to measure, am I right? So, in quantum mechanics, it's the same way. So, we're going to put operator. We have to twin. Okay, we're going to set this, all right, and then you observe, and then you're going to give us the value, and that value is called the eigenvalue energy. So what does this mean is actually something very simple. So in classical mechanics, you want to know, all right, so for example, you are Mr. Chu, definitely Chu. So you're Chuton. All right. What charge you have? What charge or what is your gender? For example, charge positive, negative. Negative. So you see, it's very sure, isn't it? It's a classical word. All right. So I try to understand physics. Doing physics is something like this. I want to understand you as a particle. So you are Chuton, and then you charge negative, right? So very sure. But in quantum mechanics, it's not that case. So same thing, right? Okay, in quantum world now, in the quantum world, so I will probe. Probe means I want to detect or want to observe, all right? Probably something like asking, right? Okay, So what are you? Who are you? Now, you are not the classical world now. You're in quantum world. So what are you going to respond? Something like this. I don't know. Yeah, something like this. I don't know. I'm not sure. Okay, something like this. You see. So could be this Chilton, correct? Maybe Chilton. Okay, Chilton. So you're going to define, and then you come to ask, what is your gender? Are you a boy or are you a girl? Or you are positive, negative? You also don't know. I also don't know. I could be boy. I could be girl. Something like this. This is quantum world. And then, more importantly, you will have this response. Okay, you feedback. You say, I don't know this. I may be this. I may be that. I can be this or can be that. Something like the superposition. All right. Something like the wave duality. Can be particle. Can be wave. I also don't know. I cannot be wave. I cannot be particle. I can be boy. Can be girl. Cannot be boy. Cannot be girl. Maybe mix or mixture or superposition. Maybe half of this, half of that. I do not know. But you will respond. But it depends on your observer. Depends on you. If you say I'm a boy, I'm boy lah. If you say I'm a girl, girl lah. Something like this. This is quantum mechanics. Okay? So everything is unsure. All right? So what you see is probability. All right? So why there's a probability? You must ask the kind of question. The probability is because we really don't know. We try to probe, right? When you probe, you have to have the camera, all right? You have to see it. When you see it, you maybe shine the light. You have to do something. But when all the things that you do, you disturb, you already change the state. We call the psi. What is psi there? Psi is actually a state, or is actually a wave function. So I believe if you want me to answer the question, what is light? I will say light is wave. Okay? Now why particle is there? Is because our detection, our observers, our observation, like we set it, we want to see a particle, then it show up as a particle. I want to see you as a girl, then you show up as a girl to me, in front of me. All right? I like you. Why I like you? Because I have this mindset, the condition there. You're beautiful. Something like this. No. This is an analogy, okay? And this guy hate you because he already set that. Now, of course, this is an analogy. You already set that kind of, the setup, the environment or the condition there. That is the observer, that you set the condition. So you only see what you intend to see. All right? So this is the wave. So what it means, the probability is something to do with the superposition. Because this state, like you can be a boy, can be a girl, can be good, can be bad. They are superposition, means they add up together, all right? And the mix you do not know. And then you try to see, when I try to see whether you are good or bad, so if I have this set up the good condition, okay, you are really good man, right? If someone has set up his own condition, his own what they call a requirement, for example, professor what and what, he will have a very high standard, right? And then he may say, oh, you are disqualified. It's something like this. I hope you understand those superposition. So the superposition means that it's overlapping, or you can think as the mixture. Because it's a wave, right? Wave, you can do a lot of these things. For example, you have the pulse. Now, how you describe the pulse? Pulse is a superposition or the mixture of many plane wave. So this is a plane wave. So for example, psi 1, you can have K1. And then psi 2, you can have K2. So all this add up. you give a pulse, and that pulse you will see as a particle. Why you see as a particle? Because my experiment set it to detect that when you have the pulse, it click. Oh, there is a photon. If I don't use this kind of condition, it will not detect as the particle. It will detect as a wave, like double slit experiment. You get it? All right. So Einstein hate that. He say God does not play die. All right. So he tried to come up with this experiment. So the most important experiment is called EPR paradox. I don't think I running out of time. So this is the EPR, means Einstein, Podolsky, Rosen, 3 person to have this thought experiment saying that if you have this, let's say a system and then explode, one particle to the left, another particle to the right, okay? And Einstein say, if I detect the position of this particle and then know this momentum, so there is no identity. That means I kill all this probability. And then Bohr said, no, you can't do this because if you observe this particle, it's going to disturb the other particle. And then Einstein said, no, this is the spooky action at the distance. Do you mean that this particle can talk to each other? And even they talk, they have to send a signal, right? Okay, hey, I got disturbed. So now you can change now. And the signal have to travel, cannot travel faster than the speed of light. This is based on Einstein's special relativity. So no object or no entity can move faster than the speed of light. So that's why Einstein really hate this idea of quantum mechanics. But they come with this experiment. I think these 3 guys won the Nobel Prize, prove that there is entanglement. They do talk to each other, but not through the speed of light, but this non-locality. When you disturb this one, immediately this is going to be disturbed. It's like your mom call you, say, what happened to you? Why I've got a bad feeling about you, or something like, you know? Yeah. So something like this is a quantum entanglement, is non-locality. Non-locality means that it happen at the same time. You don't need to have this cause and effect to do so. So this is the 3 guys won this Nobel Prize because they proved Einstein was wrong. Okay. And why is because so important nowadays? There's something to do with the application. We try to use quantum idea, quantum concept into building out this computer. So it's that like classical bit, you have very sure you have one or only one. Yes, no more, no. But quantum mechanics, you can have yes or no, or mixture between yes or no. And because of this, so we can have a lot of this information stored in actually 1 qubit. Okay. So not only this qubit can have this superposition or mixture, it also can talk to each other. So this bit and that bit can have entanglement. And what is important about this? This means that you can have encryption. So this is something to do with the cryptography. So people try to do that. So means that you cannot hack my computer. If you try to hack, try to see what is big there, you're going to disturb. You're going to write chain. Yeah, it can do so. So this is what people thought, saying that they predict if you use the classical computer super fast, to crack your password is going to take maybe a year, something like that, few months. But if you have quantum computer, it probably need few minutes to crack your password, something like this. So that's why many countries, including China, not Malaysia, Singapore, really want to work on this. Okay, of course, it has those prototype. The current state is still in its infancy, means still growing. The list here is so there are many types of the quantum computer. Some use, for example, spin. Some use superconductors. Some use ion. And some use these light source, electromagnetic wave. So many. I just go quickly for this. Of course, this is the IBM, and then they are on the market. If you want to buy one, yes, prepare $15 million, not ringgit. If you convert to ringgit, around 60 million ringgits. So they have the I think the best for 133 qubits. Of course, you see this. This is very low temperature, 0.02 K. You know how low is that, right? This is MIT one using the ion trap. So I'm going to go quickly. This is from Intel. They have this quantum dot computer. Of course, these are the top player in quantum computer. So Alibaba is there. Google also. What is this? Baidu. Yeah. I'm sure this Huawei also in there too. All right. You know these the top players, and none of these from Malaysia. So, well, I think if you're interested, it's good to plan ahead for your research, your interest. Okay, who knows, one day when there's a quantum computer, you get ready, you prepare yourself to face this kind of revolution, the breakthrough. Okay, of course, we have difficulty. One difficulty is something we call the quantum decoherence. Means that the bits that you have, they are not stable, and they are very hard to talk to each other sometimes. Now, it's decoherent because not only they can talk with each other, they also talk with the environment. All right, talk to you. So if you have a meditation, something, or go to die, go to hell, that's destroyed. People have done this kind of experiment, okay? So this is something to do with that, but mainly it's from the heat problem, the temperature. So when you have this quantum state, slightly change in environment, for example, temperature, it go destroy, mean decoherent. So we try to overcome, and all these things, only this one, this is from the Microsoft. You never heard about this Bill Gates yet, right? So he also invests in making this quantum computer. They want to use topological materials. All right. So what is the topological materials? So long. So I think they are trying to use the new particles called anion. All right. This anion is not like electron. It's not like a photon. It's something in between. Something like, is this a girl or boy? It's superposition of these two states, something like this. All right. So it's when it interchange, and it's robust. It's not disturbed by the environment. This what it means that these two particles like rotates, because one thing is phase difference, something to do with phase. So we will talk about that a bit later. Now, first you understand the topology. It's very easy to understand. It's something to do with this the shape change, right? Geometrical shape. So for example, this one, this sphere and ellipsoid are the same. So they group into one category called zero. And then you have this donut and the mark also same topologically because they have this only one hole. Okay, so they group into category called one. Say, so I think you have seen this one. All right, they can transform. Okay, so the shape will be the same. Now in the condensed matter, the topology is about the phase. So why phase is so important? You know, when you talk about quantum mechanics, phase, when you do this observation, you count the probability, the phase different from the wave itself cancel each other. All right, it's a bra and cat. If you know this calculation, because this REI alpha, okay, the cancel. So phase not play any role in the physical meaning, but not until now, because the topological has this phase important. This is a very important observation. So something, for example, the spin when it rotates, all right, move from point A and point B, you will have this phase difference, and that phase going to show up in your physical reality. All right, so I'm trying to show boson, fermion, and anyon, and all this I can write in this equation, this wave function, or the cat. Cat means this is the state. So for the fermion, you have this equation, this wave function. You must have this spin matrix over there. Spin, they call it spin node, right? Spin node. So different, you have different level, you have different energy, and this one energy you can only occupy by two electrons, spin up and spin down, right? But for boson, you can occupy as many as possible in the one state, one energy level, right? But for anyon, like I say, you can have this, you can have that. It's a superposition of both. You see? So this is the anyon. So we are trying to look for anyon in our topological materials. Okay? So if we have it, we can make this into device called braiding. These particles move around, and it will not be destroyed by our environment or noise. We can solve this quantum decoherence. So of course, this is about the phase. I'm not going to talk about that. So this is topological materials. So where is the topological material is, for example, topological insulator. So the inside, the material is insulator, but the surface or the edge is a good conductor. Not only a good conductor, is also fulfill this Dirac equation. We have this Dirac, probably you know, these high energetic particles is follow this what they call this high energy relation or energy dispersion relation. The energy is linear proportional to momentum, right? Schrödinger equation is the energy proportional to p squared. You know that energy is, the Hamiltonian is equal to p squared over 2m. So this is the quadratic function, parabolic function. So parabolic, right, you will have this low energy, but the Dirac equation, you have the linear, means you're going to have the Dirac point is linear. You can see something, the behavior, the electron behavior like this, the linear energy dispersion relation. That means is kind of like high energetic particles. So we want to see that in the condensed matter. You see, condensed matter is all about the low energy, not like the high energy particles. High energy particle is like the Dirac equation, has the special relativities equations there, right? So this three guys. Oh, okay. So I think in order to this is my field now. Okay, in order for me to have this topological quantum computer, we need to have the device called, we can have the cubic, right? Cubic to have the device to use the anion to do the what they call this counting or bit for us, right? Yes or no, things like that. They call the cubic. Now, in order to have this device, we need to have the materials. So we are in this stage. We still not have the right material for this purpose. So I've been doing in Princeton and in my school looking for this material. We have the few candidates for this. We call this topological superconductors. Of course, this is we are looking for, and so we are in the stage. It's mainly my job. So everybody is relying on me. If I get this one, they can proceed. If not, they just stop there. So something like this. So for this quantum material, we need to have the right material. So this is Bob Kawa, this postdoc advisor at Princeton. He says something like this. So we need to find this quantum material. What is quantum materials? The material must have this quantum mechanical origin. All right. So we have to understand quantum mechanics. It's a very basic. So at the moment until now, so you have heard about this quantum mechanics. How many of you understand quantum mechanics? So you understand quantum mechanics. So this is Richard Feynman, you know him. So you have something to say about quantum mechanics. If you think you understand quantum mechanics, you don't understand quantum mechanics. So I think he's trying to say is a superposition of yes and no. And then you need to have someone called observer to tell you whether you understand or not. Okay? So I say you understand quantum mechanics now. So you pass. All right, so back to this equation. So is it wave or particles? So a lot of people still think that, oh, this is the old questions and people have no interest at all. We don't have to understand. We don't need to answer this kind of question. But Einstein still, before he passed away, he still have this kind of ambiguity. He say he still did not fully understand what light is even after developing the theory of relativity. So in the letter to his friend, so all these 50 years of conscious brooding has brought me no nearer to the answer to the question, what are light quantas? Nowadays, every Tom, Dick, I don't know what it means, and Harry thinks he knows it, but he is mistaken. Still a mystery, right? Still an open question. So we still have a lot of things to do. All right. Other challenge, if you're interested, you need quantum mechanics first. All right. So you're going to talk about dark energy. Dark energy is something to do with the energy to expand the universe in the faster rate. The universe is going to expand faster and faster. Okay, and then it can expand until over the speed limit, the speed of light limit. We do not know. This is because of the dark energy. What is dark matter? Dark matter is, we do not know whether it's there or something to do with the Newtonian gravitational equation. Maybe it's wrong. We do not know, but people have observed this in the galaxy. The star or the planet in the outskirts of the galaxy is moved more faster than the prediction from Newtonian gravitational equation. And if the Newtonian gravitational force is correct, that means there must be a dark matter, right? And what is dark matter? And then you have this arrow of time, and then again you have this measurement of collapse quantum wave function. People want to know when you observe something what it means by the collapse of wave function. And a lot of things like can we unify this electromagnetic force and gravitational force? What the heck is gravity anyway? So these are from the website. They list out 18 challenges in physics. 18. I only give you 6 because I'm lazy. All right, so I'm going to finish. I take too much of the time. So this is about my physics department. So the school, Missouri S&T, Missouri University of Science and Technology, I think is considered good, I guess, because it's it has the data to prove to so top 10% of college in US, number 5 in Miami's best college for engineering major. Of course, engineering is considered good. All right, number 6. I don't understand what that. Then maybe this something is this return of how much you pay for the student fees and then you get a return, which, for example, a student they pay so much they can get a good job like 90K a year. So it's true that they have the statistics to show. The average pay for fresh graduates about 60K per year. 60K, not ringgit. US dollars, yes. Low cost, yeah. Near the big city, cost St. Louis, Chicago, 6-hour drive. It's safe. We have this partner, industrial partner, Google, Apple, IBM, Facebook. Oh, yeah. I think Boeing is very close to this. Boeing, they take a lot of the fresh graduate for building their aeroplane machine, things like that. All right. So this here is in the center. 鸟都不生蛋的地方. It means the bird will not lay egg in the area. Means very, very remote. Yeah, okay. I think a lot of these good professor. So yeah, of course, my name is there too. Yeah, Paul. This is because of the work I'm doing, the topological materials, and then very popular. People are interested. That's why I got highly cited. And the other professor is doing Kawadila. He is doing astrophysics, also kind of famous because LIGO, he is one of the team testing this gravitational wave. The big group is actually condensed matter and material physics. This is a bigger group. And then these are the research field, atomic and molecular optics, theory experiment. We have 3 faculties. Astronomy, astrophysics, we have 2. Condensed matter, you see, it's a big group. How many? 8 of them. I think the town is small. The recommended, the admission application process. Okay, so GPA is a little bit high. If you get 3, I don't know. They try to set 3.2 out of 4, a little bit high. But if you have this GI test, will be considered. If you not, it's okay. Not required. It means so you save your life, save your time. Um, I think you need to improve. I think you need to show your English is, you know, is good. So by having TOEFL or IELTS, nowadays you got many tests. So many tests you can either take online test nowadays. All right. Normally, if you accepted, you are sure for teaching assistantship. They pay very good. So I have few students from the Sri Lanka in Nepal, one Malaysia, and they went there. They immediately got a very nice car, Toyota Camry, better than mine. Okay, hopefully that's done. I think too long. I'm sorry. So you have any question? Do you understand quantum mechanics? All right, you can ask me that kind of question. You understand quantum mechanics?
Q&A session. So you are
It's okay. We want to share anything. You have any question about this graduate school? If you do not like this area, you like this one here, okay, no problem. Princeton, yes. Yes. No, no, I changing from theoretical to condensed experiment. Yeah. Yes. Yeah, yes, yes. I have the difficulty, for example. Huh? For example, I totally don't understand solid state physics. You still remember solid state physics? Blah blah, right? Yes, so yeah. Yeah, very hard. Yes. Yeah, I think it's very good questions. You touched that point. Thank you for having these kind of questions. I think I need to share this with you. Actually, I do not like to bake cake, but I do not like to do this material synthesis. Frankly, right? And then of course I face a difficulty. These are chemistry. Involve a lot of this chemistry knowledge, like how you're going to react this bismuth and selenium. All right, but this actually the chemistry knowledge from five. I did a good job in my form five chemistry. I got A. All right. I still remember those knowledge. And how are you going to have these not having those? How are you going to how for example how are you going to have bismuth 2 with selenium 3? So all everything is chemistry. And I just use my high school knowledge to solve this kind of problem. So and you ask whether I have difficulty. Of course, yes. this is only for this chemistry part, right? But for material, you also need to know solid state, like I say, and I have to go through, restudy, relearn those solid state material, also material science. For example, how people characterize these materials, things like that. I have to, I have take a lot of time to do so, and then for the experimental part, uh, of course, I just one thing I have this hand skill not for baking cake. Baking cake is different, and a lot of people's asking me, what is your secret recipe? How come you can have those beautiful crystal? How come I cannot have this beautiful crystal? And let me tell you all this experience I have. All right, this is something to do with your attitude. All right, also something like quantum mechanics, quantum behavior, quantum attitude. You must have that in for yourself. Um, you need to have observation. You need to have this kind of say picky. You have to be very serious. You have to, of course, hardworking. Everybody must have, right? So I found my student lack of something is observation, and then you just take it like, for example, granted, or maybe just follow the order without having any like patience. You need to have a passion, judgment. All right, means that you really like want to achieve something. So of course I don't like to bake cake, but what driving me is that I want to have some outcome, good outcome. I want to beat someone. I want to have the beautiful piece of art, something like this. So I just, I just, because I have this aim, I have this ambition, I have this dream. So all these are minors. All right. So it's very hard. I have to grind. I make a sample. I have to grind for hours. Grinding. Why you need to grind? So you want to have the homogeneous mixing, and you have to think very hard. Why? If you for example, if you have the solid state reaction, so you mix the powder, you cannot melt. So how are you going to have those solid state reaction? Solid state reaction means that they are not gas, they are not liquid, they're just solid, and then they can chemical reaction. Means that these elements, for example, bismuth, they can diffuse into other to combine with other elements. All right, like cation and ion. You need to think. You need to think like the atom. You need to think quantum mechanically. You need to think, oh, what happened? So, photon is like a person. Electron is like a person. They can think. Yeah, I like you. You do not like me. You hate me. So you have to think this way. You have to think like them. So, for example, you make this. Why you need to grind? The best way you grind, you can achieve the micrometer size particles. You cannot go into nanometer size. Now, in the atomic world, or in the quantum world or atomic world, micrometer size particle is like a mountain to you. You are the atom. This micrometer size particle is like a mountain, right? So how are you going to move the mountain, break it apart, right? You can't use with mechanical force. You must use heat. Heat means you generate excitation. Heat is vibration. The atom vibrate, and then it start to diffuse. Now, of course, you have the mountain. You cannot break the mountain. So only the surface is have the reaction. And then you have to keep grinding. After one heating, you take it out and then grind again. Break it apart. And then you you have to grind a lot. Means to make a good sample, you have to at least do 3 times. Grind, mix 2 hours, press it, put it in the oven, heat it up for 2 days, take it out, break it and grind 2 hours, press pellet, put it back for 3 days, heating, and then take it out, grind away, put it back at least 3 times. Then you can have the good materials. So if you do not, for example, if you do not think of yourself, you just follow the order. Your advisor asks you to do so, your professor asks you to do so. Hey, you do this, do that. And then, okay, you just do this, do that. And without thinking, all right, without observation, without like realization, you're not going to get a good result. Of course, this is the boring procedure, right? Very boring. Grinding. I feel sleepy when you grind. All right. Sometimes I grind this until midnight. I did not do 1 sample at a time. I do 10 samples at a time. Grind this up, or I put it back in time, and then I cook. I heat. I put in the furnace for 10 samples, because for one heating it takes 2 days. So the whole heating, you want to grow all this material, you need 1 week. So it's come to the question whether you are efficiency or not. So if you do 1 sample at a time, you produce 1 sample a week. I produce 10 samples a week. So I have more outcome, more results. All right, this is about attitude, about hard working. So I think you should build out that kind of attitude. You observe and then you try to think. Think when you say, think what? Think, of course, think what? What is it? Why and how? As a scientist, am I right? Okay. Why you want to do that? Why you want to grind 2 hours? Why you want to hit 3 times? Okay. And when you take out the sample, you observe, why is that? What is this? Okay, something like this. Oh, why the color change? Something like this. Okay, so you have to think. Use your knowledge that you learned from high school chemistry. Oh, white may be offside. All right, something like this. Oh, it has a contamination. So all the knowledge you learn from high school, from your college, undergraduate, do not give it back to your professor or teacher. All right. Now, of course, you have to understand. If you don't understand, it's easy for you to forget. So if you understand, then when you come to this the reality, practically, oh, you know how to solve that problem. So, for example, if you see your sample is not melting, easy, okay, heat it up, higher temperature, right? But you have to check what is the melting point for your object, all right? For example, I make this topological superconductor. You have to mix niobium, and it's very hard to grow, all right? And then you have to understand why. Oh, niobium has the high melting point. When you mix with bismuth and selenite, you're going to increase temperature. And why even you make the material, why it cannot superconduct. So all these things you have to think very hard. Now, of course, this is very boring procedure, very boring steps. Like I say, it's okay because you are having the dream, Lamborghini, Ferrari. So you work hard, all right? So you ignore those hardworking, boring steps, but you keep working for your dream, and then you have the dream come true. So even you do something else, the same. All right. So of course it's difficult to change. I have no choice. I have to build it up, and then come to this point like you as a Malaysian, we always have that kind of what they call inferior. I do not know whether you have that kind. For me, I did. All right, but after this, I have no more because my face is very thick now. I have no hair to cover my face, so you just talk to people. All right, talk to people and then get some idea. Okay, talk to professor. Okay, and then eventually you find your path. You get it. You will get it. No matter what, you get it. For example, this question, what is light? Eventually you'll get it. And I have a lot of questions about that. Not only light. I have a question. For example, what is spin? What is electron spin? And then what is charge? And I ask this question to people, and then most of the time you didn't get the answer that you want. Not because you are stupid. It's because the people is not Einstein, not Richard Feynman. You see? And then, for example, what is spin? I go and dig out myself, and then I found even the Pauli himself also did not understand spin. He just come up with this Pauli spin matrix because he tried to get adapted to the trend. They put the spin Pauli, or everything is solved, something like this. And he didn't know he didn't understand what spin is. Okay, you have question?
Particle duality. These questions are still being, researched. And recently I came across one paper.
Yeah, good.
I think.
Maybe you can share a paper with me. Chen Hao, give my email address.
Researcher is from Tata Institute of Fundamental Research in India.
Oh, very famous
Yeah.
institute.
He worked in the gravitational wave detection.
Oh, yeah.
And what he, I haven't go through the paper fully, but I heard one of his, talks in YouTube and downloaded this paper. He says that actually light cannot be wave as well as particle. There is no such thing as wave particle duality.
Oh.
And he conducted few experiments using interferometers, and he has come to a conclusion that light is a wave and cannot be said as a particle.
Good. Wow.
But these things, I'm not sure, but he is a credible, authentic researcher that I'm sure of. So I think we still need to, ask these questions again, and I was very excited to. And he has also come up with a theory called cosmic relativity. And he uses Mach's principle. There is something called Mach's principle, which Einstein was also inspired by this Mach. He was a philosopher, like that. And that's very interesting. But these questions are still being asked. So
Yeah. Sometimes we thought we understand, but sometimes people thought they understood, right? But still, a lot of things. If you try to ask that kind of question, if you work deeper and read deeper, and then you found actually we don't understand at all. Like, what is charge? Who are you? Who am I? For example, something like that. That's good that you have this paper to share. Thank you. Yeah, email me if you have the file, PDF file. I interested in reading the paper. Hey, yes.
what do you think of the development of quantum biology?
Quantum biology. Oh. Unfortunately, I don't know about biology because I hate biology. It's the But I did very well. I'm very good in for my SPM. I got A. Uh, Nowadays people try to use quantum for many field. You see, whatever you, let's say you open a company, you call your company quantum, everybody will come to do business with you, right? So name your son a quantum boy, quantum girl. Quantum biology, frankly I do not understand. I think probably they try to use quantum mechanics or quantum idea to understand biology. This is what my guess. Maybe I'm wrong because they use quantum. Quantum must be something very basics. You must have is a superposition, wave function, probability. This is the term that you need to have.
Photosynthesis. Actually, the quantum decoherence is yeah, there is no very less quantum decoherence happening in the process, the photosynthesis.
So if you think of those mechanisms, so even the chemistry reaction is also a quantum, right? Everything is quantum because if you want to see those small things like atom, you have to no choice. You have to use quantum concept. So quantum biology. What is your question again? You oh, I think yeah, it's good field. Even I do not know quantum biology, but I think it's good field because it has a quantum there. Am I right? Now, let me say. But yeah, what I want to say about this quantum. Um, if you know, if you understand quantum mechanics, you can use quantum mechanics, for example, to predict your share market. All right. I think people are trying to do so. Maybe. Everything is probability, quantum mechanics. For example, you say, is this share going up or down? It's a superposition of up and down. So you apply that, and then you apply those observer, and this observer you have to determine. I do not know, right? Because I do know about this business. So if you know some condition, then you're going to have this what they call the operator. You apply, and then you're going to know whether this is up, this share is going to up or down. So it's basically you can use quantum concept, quantum mechanics into this field. So for biology, maybe they apply the same. So you have to have operator, you must have the state, and then you might have some, eigenvalues. Those are the equations. So quantum mechanics actually is a math, is a mathematical field. So you have to apply those fields into your biology or application, business, society, and then you're going to predict Malaysia is who win the election, Najib, or who else? I don't know. Anwar. So you win or lose, superposition, or win or lose, and then you apply the operator, and then you have to know the condition, right? So what make up this operator, right? So how many people, of course. So you can also have something like this. This is all you can do is try to do the framework, and then you create your own field, quantum politics, right? I'm not sure whether you heard about this multiverse. It's actually used the same concept like superposition. Huh? Oh, you have the talk. I see. Yeah. It's actually is the idea is from the superposition. This is the quantum concept, isn't it? Every state it has a superposition of this state, that state, and this must be in a Hilbert space. Means you will have infinity of these small states you call psi one, psi two, right? And there's a no this PhD student. Well, now it's not. He actually gave up. I forgot the name. He was a PhD student at Princeton, 1960s. He's come up with this idea. Oh, there is nothing with probability. It's only that you happen in this world, you have this result. In the universe, the other universe, you have this result. And then the other universe, you have the other result. Many worlds. They call the multiverse. So the idea is from this superposition, something like this, right? Right. Yeah. For me, yeah, English. Oh, application. I think there's a shortcut way to do so. You can, let's say, contact me. If I like you, I set the condition quantum mechanically, or say, and you can come in. So that's the way. Yeah, no kidding. So if you, let's say, you want to go to Princeton University, let's say you find a professor there, right? And then you try to contact the professor and see, all right? So this is one way. Of course, you need to you need to be well prepared yourself. For example, you need to do a good job for your study, for your coursework. You have to have something to prove that you are doing good. Now, of course, for the US university, they do not know how good UM is, right? So they cannot have this standard evaluation to evaluate your result. For example, you have A, B, C, D, E, F, G, so many letter grade, right? So they do not know how to evaluate your performance. So they probably will require you to solve your GI subject test. So you need to, if possible, you have to take the GI subject test, right? Am I answer your question? Yeah. So, of course, if you really want to go to the US and you do not, let's say, need to go to a better school or whatever, there is also possibility. So, for example, you can go to the US looking for the small school, and then if the professor they want you, they can get you in. So this is more easier way, and then you try to go through their program. For example, do a master degree first. For example, like what I'm doing, what I was doing. Uh, once you're familiar with their system, once you get somehow well prepared with your background, right? Fundamental knowledge in physics. So, and then people will start to know you or recognize your performance, so you can go to a better school. So some school they may also offer master only. They don't have PhD. So go to the school, for example, get a master degree, and then from there you go to the PhD programs university. So this is also one way. Okay. So for example, I took 2 to 3 years to prepare myself. Actually, that was what I call this blind way to do. I did not know there's other way. I just follow one way, right? Just get the good result, but you don't have to sometimes. Not necessary. Some some of my friend, he just ignore this way. They go through other way without taking any GRE tests also. So there's other way. I think America is much. I think it's much easier in the sense that they have many university, like 2,000 university, so you can try some small school first, doing the for example master degree, and then try to build out yourself, and go to the better school. So of course the difficulty for the PhD program in the US, you need to really master the knowledge for your graduate course. For example, you need to pass your qualifying exam, right? If you fail one time, you still have a second chance. But if you fail second chance, they'll say sorry. You only have master degree. You are not allowed to be a PhD candidate. Means that you cannot do any PhD research. You got the idea? So my advice for you is that try to go to a small school. Immediately just build up yourself, like learn, study, prepare yourself for PhD qualifying exam. You need to pass the PhD qualifying exam. This is the first step. It's not like the UK. UK does not require you to take the test, right? The exam. Only the US need you to pass the PhD qualifying exam. This is most difficult part. Once you pass, I think everything will be smooth. You just concentrate on your research. Finish it up in 3 years. Then you got the degree. Yeah. Yes. Do you have? Oh yeah, USM. This question. You're asking, is there Malaysia university better than the US university? So where are you from? Yeah, sorry. Oh,
better in Malaysia than in US. Then you regret like going out of country research.
oh, no regret. Well, actually, when I uh, this is a very long story, right? If you have time, be patient. I'm sorry, I speak very soft and slow, but be patient. Um, this is interesting story of my part. Actually, I have those professors encourage me to go abroad to the US or to the UK. Well, that time I did not like to stay in America because the influence from the news saying that America is bad, is it's a bad culture, things like that is not good, things like that, right? So because I want to have the study a PhD, I want to I want to fulfill my dream. So I went to America, uh, saying that I finished the PhD and I I want to come back to Malaysia and then to teach in USM. Was my dream because my hometown is Kepala Batas. So the only university in Penang is University of Science Malaysia. So this was my earlier plan. But somehow I went there, like I saw you, the first impressions, all the three dead. All right, but the people there are very friendly. It's like if I walk on the street, right, someone came by and then, oh, and saw me and then said, hi, how are you doing? Things like that. I was shocked and do I know you? Now ask myself quietly. I did not know the person, but they say hi, how are you? Things like that on the street. And it's stranger. All right. And then also I got a car that time and my car broke down because I bought it cheap. It's $1,200. So used car and it's broke down on the street. And then I try to figure out what's the cause of the problem. And then someone came by. I think he was the Indian. I think not in I mean the local, what they call the red Indian. He was wearing very clean and white long shirt. Yeah, Native American. Thank you, Native American. And he passed by and saw me the car, and then he said, "Oh, do you need help?" I said, "Oh, I think no, I'm fine." Because it's hesitation to ask someone to help. So I tried to figure out the problem, but he stopped by and then checked for my car, and he told me that he has a little bit knowledge about car repairing, and then he asked the question, "Oh, what's the problem?" I said the car cannot start. Oh, he said maybe about this fuel pump, and then he went underneath the car, white clean long sleeve shirt. Went underneath. I did not went underneath my car. I say it's dirty floor. You went underneath and claw in and see. Oh, you try to start. Ask me to start, and then he checked. So this is the first impression I had about America. It's not like this America is bad, things like that. What we heard from the newspaper, all right. So the people there is really helpful, and I as a Malaysian I hesitate to ask questions, but they encourage me to ask questions, and they no such thing, no such thing that the teasing like your English is bad. I got a lot of teasing from my friends. Even I speak Mandarin, they also tease me. Why you speak lousy Mandarin? Things like that. But American, they did not say such kind of bad word to me. They said, "Oh, how come your English is good? You can speak 5 languages. I can only speak 1 English." All right? They have the kind of the attitude, the kind of culture. They respect you, something like this. So you say did I regret? Probably no. And why I did not come back? I'm not sure whether you have that kind of question. I wanted to come back actually, all right, but I got family. Later on, I got family. I got 2 kids. They were born in the United States, and also another story because the government support them. I have no money to support 2 kids, and I didn't even know that I can have 2 kids while I'm doing PhD degree. So my 2 kids were born when I staggering with this baking cake. and they got a lot of support from the US. So I don't have to pay a single cent to buy their susu. So and then they grow up, they like to stay in America. I asked them to come back to Malaysia. And they're happy to go to school. I don't understand. I did not understand why I asked them why you are interested to go to school. When my time, I hate to go to school. These things. So they grew up there. So I kind of like, oh, I I cannot come back. This is like something's the confusing part of me, right? It's a quantum mechanics. Come back, superposition, come back, or don't come back. So if you come back, you kind of feel sorry to my kids, right? If I don't come back, I feel sorry to my parents. You see, my parents are here. They're still here. So there's a mixture of these two feelings. It's a quantum mechanics. Superposition of coming back or not coming back. They did observe, yes. So I set up the condition observe, so I stay in that and then may come back to help you guys. I hope to help in this university. So have a collaboration. That's why I'm here. So this is a superposition of back and not coming back. Am I answering your question? All right. So what's time now? Good. 6 o'clock.